So this is electrical machines too. Okay. Here, this is taken by Professor T.K. Bhattacharya. Now, this electrical machines has two part. One was electrical machines one, which took place in the last 6 months. Okay, the from September to December, it was taken. So there, I was also one of the TAs. So there, I discussed the DC machines and the transformers. So in this electrical machines too, we will be focusing on synchronous machines and induction machine. But before going into the synchronous machine and induction machine, okay, so I'll be discussing for this assignment one. So let us wait for everyone to join. Okay, okay. Just let us wait for some time, like maybe 1, 2 minutes, so that if people are joining, they can join. Okay. Because otherwise I'll be speaking there and in between people will be coming, so then it will be a little bit difficult for others to then um, see what happened, what was discussed earlier. Okay. Okay. So I'm starting the lecture. So here in this this is electrical machines 2. So this electrical machines has two parts. Okay, electrical machines 1 and electrical machines 2. So in this electrical machines too, we will be discussing synchronous machines and induction machines. Electrical machines was already taken in the last 6 months, which was from September to December. Okay, so there the main focus was DC machine and transformers. In this electrical machines too, the main focus is synchronous machine and induction machines. Okay, so this is the assignment one. Now you will see that in the in the first week of lectures, professor has discussed some things on transformers also. Okay, and the assignment one is mainly on transformer action. Okay, so I'll be discussing transformer action, and then we will gradually be shifting to what you say one conductor in a field. Then we will be applying our concepts to induction machine and synchronous machine. Okay, so here we are starting first with the transformer. So let me make this like this, and let me hide this. Okay, so here, um, okay, other people are also coming. Okay, so I can see many of the familiar faces also from the last time. Okay, so so this is electrical machines too. So this electrical machines too, we will be seeing the induction machines and synchronous machines. In electrical machines one, and I can see some familiar faces. So they have maybe some of you have done the last electrical machines one where we discussed the DC machines and the transformers. Okay, so in this electrical machines two, we will be focusing on synchronous machine and induction machine. But for this assignment one, you will see that the couple of lectures like lecture one, lecture two, and I think somewhat lecture three also of the professor in the first week is focused on transformers, and the week one assignment is basically on transformer. Okay, so I'm discussing transformers basics. This is already discussed in electrical machines one also, but I'll be again discussing it. So, okay. So then let us start with the discussion. So, so the topic here which I'm discussing is transformer. Now, what is a transformer? Transformer is a static device, right? It does not have any rotating parts. So, transformer is a static device. So, you will see that like DC machines, okay. Mm, what was it? Okay. So, you will see that DC machines, induction machine, synchronous machine, all of these, okay, are rotating devices, right? So there are two types, okay? So first of all, if someone says that, uh, so this is basically electrical machines. Why this is electrical machines? Because it has rotating parts also, okay? Because electrical is short for electromechanical, okay? So electrical is a short form of electromechanical machine. So that is why, so you, if you see by the definition, transformer is not exactly an electrical machine because it does not have electromechanical movement, right? In DC machines, what you have? So in DC machines, you have a field, okay? In all kinds of machines, in some or the other forms, you have a magnetic field in which a conductor is placed, right? And this conductor is made to rotate, or this magnetic field is made to rotate, either of the thing, okay, depending on the machine. So you will see that, so as per the Faraday's law, so Faraday, he said that EMF is induced whenever there is rate of change of magnetic field, okay? So there has to be a rate of change. Now you will see in this DC machine what happens. Um, so someone is saying something. Okay, so not sure if it only me, I can see the screen. What you are saying. Can you please reshare? Okay, just let me then share it again. I don't know if this problem is for everyone or not. Okay, so let me share. Uh, where is it? Entire screen. Share. Okay. So I hope you can see this. Are others able to see my screen? Someone please confirm either by speaking or by writing. Can you see my PPT which I am sharing and then I'm writing here? Can you see this? I'm actually sharing right now and then I'm also writing here. Okay, so you can see, right? Okay. So, um, okay. So as I was saying here, that here what we have is that this is a transformer, right? So transformer is a static device because it does not have any rotating parts in this, okay? So we will see that in most of the machines, DC machines, induction machines, synchronous machines, when they're acting as generator, so what happens is that there has to be EMF induced, right? For a generator, what should happen? There has to be EMF induced. So we will see that as per Faraday's law, EMF is induced whenever there is a rate of change of magnetic field. Okay, so rate of change of magnetic field. So how can this rate of change happen? It can happen in time, okay, or it can happen in space. So what do I mean by this? I mean that let us take an example of space. Okay, that rate of change happens in space. So here you will see that this magnetic field. So let us suppose we place two magnets, one north with its north pole on this side and south pole on this side. So what will happen? The magnetic field lines will be produced like this, right? So magnetic field lines are produced. However, these magnetic fields are stationary, right? These are magnetic fields which are stationary. Now, what we will do is for creating the rate of what you say rate of change, what we will do is the conductor which we have placed in this magnetic field, we will rotate this, okay? So if we rotate this, then what will happen is that since this is rotating, so it will experience a rate of change of magnetic field. Now magnetic field is in one place only, but the coils are basically rotating and cutting the magnetic fields. So what happens that so for a coil, if you're sitting on a coil, you will see that the magnetic field is changing, okay? So that is how the rate of change of magnetic field is made in DC machines. Okay. And we will see that in the incoming lectures for synchronous machine and induction machine, how this rate of change is created. Okay, so you will see that in these DC machines, induction machines, synchronous machines, the rate of change is created in space, meaning you use a prime mover to rotate the, so you will see that these three machines have stator. Okay, so they have a stator like this. If it is synchronous machine, so it is like this, and then they have a rotor. Okay, so this is for the synchronous machine. Similarly, for induction machine also you have some other diagram. So you will see that in all the machines you have one stator part which is stationary, and one rotating part which is rotor. Okay, now this rotating part is made to rotate. Okay. Hmm. So this rotating part is made to rotate by using turbines. You will see that in our, if you go to any power plant, so you can go to two types of power plants, right? So you can go to thermal power plant where we use coal, we burn the coal to produce steam, so that steam is made to put on these coils, so that so this rotor parts rotates. Okay, so thermal power plant, what we do is we use the basically steam which is produced from the coals to rotate this rotor part. Okay, now if you go to hydel power plant, you will see that the at the where there is water is made to fall from a height like a waterfall or something, so the water is made to fall on the turbine blades. Okay, you will see that where there are various kinds of turbine blades like Pelton wheel and all that. So that is not the part of discussion, but just try to understand that we rotate the rotor part in these machines by either using the gravitational force of the falling water or by using the heat energy of the coals. Okay, which produces the steams. So in this way we rotate the rotor part so that we can create this rate of change of magnetic field. Okay, so in some cases the coil is made to rotate. In some cases this magnet this what you say, this permanent magnet or this arrangement is made to rotate. So we will see in our upcoming discussions. Okay, but just for now try to understand that there is a rate of change of magnetic field in space. Okay, so that is what I wanted to say. Now coming back to the transformer. Okay, so if we come back to transformer, you will see that see there is no rotating part. Okay, so there is no rotating part means okay, let us admit the people. Okay, so since there is no rotating part, so there has to be some rate of change of magnetic field. So for producing this rate of change of magnetic field, we provide an AC voltage source. So AC voltage source. Okay, so AC voltage source means this EMF which is provided at this primary winding. So you will see in the transformer there are two windings. Okay, this is a primary winding and then there is a secondary winding. Now, if we suppose we want to transfer the power from primary side to secondary side, so what we will do is we will provide the AC source at the primary. Now, why we cannot provide a DC source? Why we need an AC source? So why we need an AC source is because you will see. So let me put this transformer on the next slide also. Okay. Okay. So here, so this is the thing, right? So this is our transformer, coming back to transformer. So here, what we will do is we will create a rate of change of EMF in time. So for that, what you will do is you will give an AC source. Okay. So AC source means if suppose this is E1, this is E1. So E1 is like this, okay, with respect to time. So with respect to time, it is like this. It is like you can see it is sinusoidal, right? So sinusoidal means it is changing with respect to time. Okay. So this is the situation of E1. Now, let's come back here. So, how does this transformer action takes place? Now, because you have provided a voltage source, now because of this voltage source, the current will flow, right? So, current is flowing, then current is flowing like this. Do you agree that current is flowing like this? So I hope you can appreciate that if you apply the voltage source, so because of this, if we assume this as the positive at some instant, this is at positive, so at some particular instant, this is like positive voltage. So current is flowing in this way. Okay. So current is flowing in this way. So like this current is flowing. Now let us see that if suppose we apply this right hand rule, okay, right hand thumb rule. So what does this right hand thumb rule says? So right hand thumb rule you can apply to a coil. So suppose you have a coil like this and a current is flowing in this way. So what will happen is that if you place your hand, right hand, in this thumbs up action, okay, so if you make your hand in the thumbs up action, so the thumb should point towards the current direction. Okay, so the thumb is pointing towards the current direction. Then the curl of the fingers, the curl of the four fingers will tell you the direction of the magnetic field. Okay, so this is the magnetic field lines. This is how the magnetic field lines are flowing. Okay, now if suppose you have a solenoid, okay, so this is a solenoid on top of which you have wound your coils, okay, coils of the conductor. So in this case, how you will apply the right hand thumb rule? So for applying the right hand thumb rule, you will curl your four fingers in the direction of the current which is flowing through the coil. So this is like this. Okay. So suppose this is the coil like this. Okay, let us say this is the coil like this. So suppose this is the direction of the current. So what you will do, you will keep your four fingers. Suppose in the right hand, you have put your right hand in the thumbs up action. So the four fingers are along uh, this rotation. Okay, so this is the four fingers of your hand. Okay, like this. So four fingers are like this as shown in this hand also. And then your thumb will give you the direction of the magnetic field. So this thumb here will give you the direction of magnetic field. So you can see that the thumb is pointing upwards. So it means that the magnetic field is upwards. Okay. So magnetic field is upwards in this case. Okay. So here this is your magnetic field direction. So this is the right hand thumb rule. Okay. So is there any doubt till now? If there is any doubt, so please get it cleared because you have to solve the question. So you need to get your doubts cleared. Okay. So if there is any doubt, then please speak up. Till now, whatever I have discussed regarding the right hand thumb rule and this basics of Faraday's laws, if there is any doubt, then please speak up. Okay. Okay. So now let us come back here. Okay. So here this is the right hand thumb rule. Now we will be applying the right hand thumb rule to this coil. Okay. Now you can see here that if you apply the right hand thumb rule, so can someone tell me what will be the direction of magnetic flux here? Whether it will be upwards or whether it will be downwards, can someone tell me by applying the right hand thumb rule to this current carrying coil solenoid? So keep your four fingers in the direction of the current arrows. You can see these arrows, right? Of the right hand. Then your thumb will tell you whether the magnetic field is upwards or downwards. Okay. So just tell me downwards. Correct. So the magnetic field is downwards. Okay. So so this is not the case. So if you do this, you will see that this is downwards. Okay, so this is downwards like this. So this is your magnetic field. Okay, so if I draw the magnetic field in this diagram, so this is phi. Okay, so um so this is phi. So I'll if I draw the phi, so your phi is like this in this diagram. Okay, so this is the phi. Now, so let us say that phi is phi m sine omega t. So if we see the EMF, if EMF is induced, EMF as per Faraday's law is what? It is rate of change of flux linkage. Flux linkage is denoted by lambda, where lambda is n is the number of turns into phi. So because we are seeing the suppose EMF induced for this E1, so this is this is V1. So let me draw this. Okay. So, 1 minute. Hmm. So here you will see that the flux linkage is number of turns into flux. Okay. So let us say we want to find E1 here. So this is suppose E1. Generally, E1 is denoted by induced voltage by the Faraday's law, and V1 and V2 are denoted as the terminal voltages. Okay. So you will see these are the conventions, though you do not need to worry because these conventions are not exactly asked in this assignment. Okay, just the basics of transformer for this first week assignment. Mostly we will be discussing the induction machine and synchronous machine. Okay, so this is lambda equal to n phi. Now d lambda by dt is suppose E1. So d lambda by dt. So d by dt of n into phi m sine omega t. Okay, so what does it give me? It gives me n phi m omega cos omega t, which can also be written like this: n phi m omega sine omega t plus 90 degree. Okay, like this. So this is the thing. Now here, if I show you this, that so if I calculate the RMS value of this E1. So RMS value of E1 is what? Because this is the peak value. So you can appreciate that this is the peak value, right? So the relation between the peak and RMS for a sinusoid is like this, that if suppose your peak is A in A sine omega t, then your RMS becomes A by root 2. Okay, so n phi m omega in by root 2. So you know what is omega? Omega in terms of f is 2 pi f divided by root 2. So this becomes root 2 and this becomes root 2. So this becomes root 2 pi f pi m n. So if you do root 2 pi, you will see that it comes out to be like 4.44 factor. You would see this 4.44 factor, right, in your classes earlier. So if you do this root 2 into pi, so you will see this is 4.44. Okay, so this is 4.44 n phi m f. So this is the RMS value of E1. Okay, and this is in terms of N1, remember, because the flux lines are linked, we are talking about E. So here the N, we want to see the flux lines which are linking this N1 turns. Okay, so everywhere this has to be N1. Okay, so this is N1. Now similarly, you can do it for n2 turns, like the second turns. Now an interesting thing comes into picture. Okay, so what is the direction of EMF which gets induced? And we will see the dot polarity. Okay, so let us say this is the positive terminal. So let us say that positive terminal is marked here with a dot. Generally we place the dot at the positive terminal. Now we have to see that whether the EMF induced here is like this or like this. Okay, so we have to see that. So for seeing that, what we will do is we will place the resistance here like this. So let us say that we are taking the first case, which is this minus plus. So if this is minus plus, so how will the current flow? So current has to go out from the positive terminal and enter the negative terminal, right? So the current is going out from positive terminal like this, like this, like this, like this, like this. Okay. So if you apply here again the for this right hand thumb rule, like so this is the current flowing in these coils. So first of all, we have taken this. If suppose we are considering that the here on the secondary, this is the what you say EMF induced. Like let us say the EMF is induced like this, and the dot is at the bottom. Let us say for the first case, okay. So we know that the current leaves the positive terminal and current enters the negative terminal. So we are thinking that okay, so the current is like this, okay. So if we think that the current is like this, so you will find that for this direction of current also, the magnetic field is like this. Okay, so you will see that the magnetic field is downward, right? So what is happening? So this magnetic field and this magnetic field, they are opposing, is it not? So, so you will see, so, so this is the phi produced due to this secondary winding. Okay, so this phi secondary and this phi primary, they are opposing, right? One is like this and one is like this. So so this is correct, right? Why this is correct? So I will tell you. Okay, now let us say the other example. So let us say if suppose we consider that okay, no, the dot is not down, the dot is up. Okay, so if the dot is up, so this becomes like positive, negative. So for this case, the current will what you say leave the positive terminal like this, right? Or am I saying something wrong? Let me just see this. Okay, 1 minute. Okay, so I made one mistake. Okay, so let me tell what my mistake is. Okay, so इसको हटा देते हैं. First of all, we want our fluxes to be like this only. Okay, that this is okay. Our phi primary is like this, so phi secondary should oppose it. Why it should oppose it? It is because of the Lenz's law. Okay, so what does the Lenz's law say? Let me first write it. So so Lenz's law I'm writing. So according to the Lenz's law, because it is Lenz's law is nothing but what is this? It is the law of conservation of energy. It basically says that energy cannot be created, neither be destroyed. It can just be converted from one form to another. Right. So basically, here what we are trying to do, we are saying that okay, so this is the amount of energy which we have applied. So that amount of energy will be consumed for inducing the EMF here. Right. So that is why this phi secondary is opposing the phi primary because it is trying to what you say trying to oppose the cause. So the cause was this flux phi. So it is trying to oppose this cause. Okay. So it is so effect is trying to the effect which is the current which will flow. So current should flow in such a way that it should oppose this basic flux. Okay, because if suppose if you do not agree with that, then what will happen, that this flux is there, then if you think okay lenses not does not work, so what should happen is that current should flow in such a way that this flux and this flux should add up, so the effective flux will increase, right? So the amount of magnetic energy is increasing. That should not happen, right? Energy cannot be created. So that is why so that is why to balance that, the flux secondary should be in such a way that it should oppose this flux primary. Okay, so I'm writing that only. According to Lenz's law, so इसको hide करो. According to Lenz's law, direction of induced EMF. Okay, is such that if it is allowed to cause a current in secondary winding, okay, then the current so produced would have an effect, would basically oppose the cause, okay, would oppose the cause. Basically, law of conservation of energy. So this is important, okay? This you will see that from using Lenz's law, even in the DC machine, induction machine and synchronous machine, DC machine we will not discuss, but you will see in the other machines, we will be deciding how the EMF is getting induced, okay? So here, so this is the case, okay? So you will see that, okay, so we want our phi secondary to be opposing. This is the phi secondary which happens in the nature. Okay, this is acceptable by the nature that okay, and if phi secondary is not adding up, it is opposing. If it adds up, then it means that energy is increasing, which should not happen. Okay, so the phi secondary is like this. So what should be the direction of current then? So the current is clockwise or anti-clockwise? So you will find that the current has to be clockwise like this. Okay, so current is clockwise means the current is like going in like this and coming out like this. So we have to find that okay, the from where the current is coming out, there we have to place the dot. It means that because current, if suppose you connect a load, if suppose this is the load, suppose I am representing this coil like a voltage source. So for current to come to go like this, the positive should be on the top, right? So if the positive has to be on top, it means that this dot has to be on the top. Okay, so this is like this. Is there any doubt? Because this was a very important concept. So it has to be clear, okay? Because you have to even aside from solving the problems, if someone asks you, then you should know these things, right? So is this clear? So I hope this is clear. Okay, good. So if there is doubt, please speak up. Okay. Otherwise, the doubt will remain. Okay, like this. So now this is how the flux should be. Now we will see what you say. The E2. What will be the E2? Okay. So let us say this is like this. Pen. Okay. So I will be writing for E2. So what will be E2? E2 will be d lambda by dt, where the lambda will be n2 into phi. N2 is the number of turns, N2 number of turns for this. So E2 will be the rate of change of flux like this, and similarly you will get E2 is equal to N2 phi m omega sine of omega t plus 90 degree. And if I talk about RMS value, then RMS value of E2 will be 4.44 into phi m f in a similar way. Okay, so E1 like was like this, so E2 is like this. Okay, so you will see that this E1 by E2 is equal to N1 by N2, right? So E1 is directly proportional to N1, you can see from here, and E2 is directly proportional to N2, RMS value. So if I take the ratio of this RMS value, it is dependent on N1 by N2. Okay, so this we will be using for solving the questions. Okay. Now the other thing is the MMF balance. Okay. I think the MMF balance part is not that much necessary, because professor has also not discussed it, because that is actually the part of electrical machines 1. Okay. So electrical machines 2 is mainly focused on just the basics of transformers, this ratio, so that we can solve the questions. Okay. Now, I'll be discussing some of the things which the professor was discussing in his lecture. Okay, so that you can correlate the lecture with the things which I am discussing here and get your doubts cleared. Okay, so coming back here, so let me use this, I guess, pointer. Okay, so this is the some of the things which sir has discussed in his lecture 1, week 1. Okay, so you will see that this is the equivalent circuit diagram of the transformer. So if I draw the equivalent circuit diagram of the transformer, okay, so first of all, there is a no load part. So has the professor drawn the no load part? Okay, he has drawn the no load part. Okay, so I'll discuss little bit on the no load part. Okay, so questions are very simple for this assignment. If you understand these things now, the questions are like very easy. Like it will, you will solve those questions like butter. Okay, so let me um, draw this. So if suppose we take a ideal transformer, okay, ideal transformer. Now, in an ideal transformer, we will be assuming some things. Okay, it may ask you some theory question that what are the assumptions made for an ideal transformer. So the first assumption is that there is no losses, and the second is that this nu is infinite. So you will see that flux, which is MMF by reluctance. So MMF by reluctance means Ni by S. S is generally used for denoting the reluctance. So S is the length of the magnetic field path divided by nu, which is the magnetic permeability, and the cross-sectional area of the magnetic medium. Okay. So if suppose nu is infinite, then for producing this phi, the what you say, you will see that the amount of current required will be very like negligible. Okay, so you will see that the amount of magnetizing current required for setting up this magnetic flux will be zero. Okay, this is the case of ideal transformer. Okay, so if suppose if someone asks you what are in the question, if suppose theory question something is like this, that what are the assumptions of the ideal transformer? So the first assumption is there are no losses, like there is no copper loss. Copper loss means I square R loss. There is no core loss. Core loss means iron loss, means the hysteresis loss, eddy current loss, all that. Okay, there are no losses, and the magnetic permeability is infinite, means that you do not require to even give any current. This is ideal, right? Nothing is ideal in the universe. But in an ideal transformer, it is saying that the reluctance is this magnetic field is so good that you only by giving like very small current which tends to zero will set up the magnetic field in the transformer. Okay, so this is the ideal transformer assumptions. Now let us write the assumptions for practical. So in the practical transformer, there are no such assumptions, which is the because practical is an actual system, right? So this is practical transformer. Now for a practical transformer, you will see that if you have seen in the earlier case, we drew this E1. So E2 is also in phase with this E1. Okay. So if I draw E2 on top of this, you will see that E2 is also like this. Okay. So E2 may be like, suppose if N2 is less than N1, so E2 magnitude peak will be less. Okay, like this. So this is E2. So if I draw the, what you say, this phasor diagram for this, you will see that this is E1, E2. Okay. Mm, this is, इसका color क्या है E1 का? Red, right? Uh, okay, so let me this is not E2. This is basically the phi thing, right? So let me see. Okay, actually this red one is supposed to be phi. Do you understand? Because phi is sine omega t, right? So, so I'm just, can I erase this? No, I cannot erase this. Okay. So let me just do this. So you will see something. You will see that this phi is phi sine omega t, right? So sine means what? Sine means the at the or the starting point it should be zero, right? This is a sine waveform and this green one is a cos waveform. So the red waveform should correspond to your basically phi and the green one should correspond to your E. Okay, because it is a cos waveform. Because from all these things, it depends on what you are taking your phi as. Okay. So it totally depends on that. So you will see that this E1 is a cos waveform. So you see this E1 here is the cos waveform. E2 is also a cos waveform. Sin omega t plus 90 is cos, okay? E2 is cos and phi is sine. Okay, so you will see that here, let us say that this is phi. This is your green one, let us say is E1. So this dark blue one is E2. Okay. So dark blue one is E2. Nothing to just worry about. It's just that whatever I have obtained, like E1, E2, phi in terms of sine and cos, I'm just drawing that. Okay. Now you can see that because phi is sine and E1, E2 are cos. So E1 and E2 are basically leading the phi, right? So this is E2. So this is E1. They are leading the phi by 90 degrees. So let us say phi is red. So phi, they are leading by 90 degree. So this is the phasor diagram of the ideal transformer. E1 and E2 are in phase. Okay. Their magnitudes may be differ depending on this N1 by N2 ratio, but they are in phase. Okay. And phi is lagging by 90 degree. So coming to the practical transformer. So in the practical transformer, it is like this. So here you have phi. Okay. E2 is again, I'm just taking 90-degree leading in this way. And E1 is here. So this till here, this is common. But what is different is the different part is here now. Okay. So you will see that this no load current. So earlier there was no, you will see that no load current was not needed. Okay. But now the no load current is also coming. Why? Because this I naught was zero for initially setting up the magnetic field. And so you will see that I naught has two parts. Okay. I naught has I magnetizing and it has I core loss. Okay. IC. So this, because there are no losses, all the core loss and everything is zero. So IC was zero and IM is zero because the amount of current required for a magnetic medium which has nu equal to infinite is zero. So I naught was zero, but right now the some I naught is there because there are losses in the system and nu is not equal to infinite. Okay, so that is why I naught is coming. Now I naught is having some angle with like this phi naught. Okay, so this is the core loss component of the no load current. So this is no load current. Okay, so this is having a core loss component I naught cos phi naught, and this is having the basically magnetizing component which is Im I naught sine phi naught. Okay, so if I draw the equivalent circuit diagram, so for the equivalent circuit diagram, so for the two windings, I am basically first drawing like this. So you know that there are two coils. So the two coils are having some inductances associated with them. Primary inductance is L1, secondary inductance is L2, and there are some resistance because everything in the nature has some resistance to it, right? So let us say that the resistances are R1 and R2 respectively. Now, if I draw the equivalent circuit diagram for this, okay, for this magnetic part in between, Okay, so this is R1, L1, L2, R2, and this is basically RC and XM. Now XM has the current IM passing through it, and RC has the current I basically IC passing through it. Okay, so this RC represent the core loss component because you see this is the core loss means magnetic losses. Core matlab magnetic losses. Okay, hysteresis loss and eddy current loss. So you know that the in phase component basically cause, if I have to find out the core loss, so it will be something like E1 into IC, E1 I0 cos phi naught, right? So it will tell me that okay, the core loss component is the cos phi naught component. So that is why, because it is in phase, if you take I naught cos phi naught, so it will come in phase. So in phase means, so it, because it is an in phase component, it is represented by resistance. However, this Im is lagging by 90 degree. So which component in which component the current lags by 90 degree? You will see that in the inductance the current lags by 90 degree. So that is why Im component is represented by this Xm, which is inductance. Okay, so inductance represents Im because this current is lagging this E1 E2 by 90 degree, and this IC component is represented by the resistance because in here this IC is in phase with E1 and E2. Okay, is it clear? So you will see that the professor has drawn this diagram here directly. Okay, because this is part of electrical machines 1. Now coming here, what the sir is discussing it, he is discussing the how to find these values of L1, L2. Okay, so L1 how we will find out, let us see. So L1 means what? If you see the formula of inductance, inductance is nothing but the total flux linkage lambda by I1. So what is the flux which is linking this winding? Okay, so let us say this flux phi is the one which is linking the windings N1. So this flux becomes N1 into phi divided by I1 because N1 is the number of turns for this winding. Phi is the flux which is linking to the winding. And why the flux is there? Flux is there because of this current I1. Okay, so that is why N1 into phi by I1. This flux has two parts. One, so you will see that the flux, any flux in the nature will have two parts. Okay. So I'm just drawing the flux lines. Okay. So there will be some flux lines which will be linking both the coils. And there will be some flux lines which are just leaking in the nature, leaking in the air. Okay, so these flux lines which are leaking in the air, which are not linking any winding, this is called as leakage flux, phi L1, and this is the mutual flux, phi M1, which is linking both the windings. Okay, basically this N1 turns and N2 turns. So this part of flux is phi M1, and this part of the flux is phi L1, which is not linking the two windings, it is only linking the one winding and the air. Okay, so these are the two parts, phi L1 and phi M1. So that is what the professor has also written here, phi M1 and phi L1. This phi has two parts, phi M1 and phi L1. So here that is why he is replacing the phi, which is the total flux, which consists of the mutual flux and the leakage flux. Okay, so N1 into the mutual flux plus the leakage flux divided by I1. Why? Because this phi in the first place was produced because of the I1 current passing through these N1 coils. So that is why N1 by I1. Okay. So N1 into phi M1 by I1 plus N1 into phi L1 by I1. So you will see that this corresponds to leakage inductance. Okay. And this is the inductance which you will see is called as mutual inductance. Okay. So this is leakage inductance. So this is leakage which sir has already written, and this is mutual inductance. Okay. Now, in his next slide, you will see that in his next things which he has written down, what all things he has discussed. So similarly, he is finding out for the N2 number of turns. Let us say the I2 current is passing through this N2 coils. Let us say we are, instead of giving the input here, input at the primary, we are giving the input at the secondary, let us say. Okay, so if we give the input at the secondary, then what will happen is that here this flux will also, so this L2 will be what? L2 will be the flux which is linking this secondary coil. So secondary coil has how many turns? N2 turns, and this flux was phi 2 was produced due to the current I2. So N2 into phi 2 by I2. Now this phi 2 also has two parts, one which is linking both the coils and one which is leaking in the air. Okay, so that is why phi 2 has two part, phi m2 plus phi l2. So here instead of phi 2, the phi m2 and phi l2 is placed. So this gives you the leakage part, and then again here you have the mutual part. Okay, so this is the mutual part and this is the leakage part. Okay. So now he will try to find out what is this mutual part. Okay. So for finding the mutual part, what he has done is, so let me go here. So he's saying that, okay, M21, which is basically the mutual due to the current flowing in this N1 turns because of the current I1. Oh, sorry, I'm mistaken. So what I'm saying is that here M21 means 2 means the basically the mutual inductance in the secondary winding due to the current flowing in the primary winding. So the second position denotes the current in which winding. Okay. So similarly here also 2 means current in secondary winding. Okay. So you will see that 2 means the क्या कहते हैं, mutual in the second due to the current in the first winding, M21. So because this is 2 basically on the secondary winding, so we have placed the number of turns as N2, and current, because it is current is due to the primary current, we have placed the current as I1. Okay, similarly here you will see that in M12, because this number of turns on which the, because mutual is on 1, so mutual is on 1 means we have placed that number of turns as N1, and the current because of which this mutual is there is 2. So this is I2. Okay, like this. Now we will see, because okay the current is I1, so because of I1 there was phi M1, right? क्योंकि जब I1 था, you see, because of this I1, because of this I1, this phi has phi m1, right? So that is why with I1 we write phi m1. Okay, and with 2 we write phi m2, because when we are talking about I2, because of I2 there is phi m2 which is passing through n1, right? यही तो हमें देखना है ना कि ये जो phi m2 जो पास हो रहा है N1 से, यही तो म्यूचुअल देगा. फाइव एम टू क्यों पास हुआ? फाइव एम टू पास हुआ क्योंकि करंट I2 फ्लो हो रहा है, पर हमें किस में देखना है? वी हैव टू सी इन दिस प्राइमरी वन विच इज द N11. Okay, so that is why we write this mutual as M12, mutual in 1 due to 2. So mutual in 1 means how many number of windings it is linking? It is linking n1 number of windings. But this is which flux is linking the n1 number of windings in mutual? This flux phi m2 which is due to I2. Okay, so that is why this is written as N1 into phi M2 by I2. So in this phi M1 is what? Phi M1 is N1 I1 by reluctance, right? क्योंकि phi M1 कैसे कैसे पास हुआ? So if phi M1 if we see, phi m1 is what? Phi m1 is because of n1 number of turns, क्योंकि n1 number of turns में से I1 पास हुआ, इसलिए तो phi m1 आया, इसलिए n1 I1 by reluctance. ठीक है, तो यहाँ पे phi m1 की जगह इन्होंने n1 I1 by reluctance he has placed, and in place of phi m2, because phi m2 is because of this I2 flowing in n2, so this is n2 I2 by reluctance. So n2 I2 by reluctance. So if you place this, you will see that M21 comes out to be N1 N2 by reluctance, and M12 comes out to be as N1 N2 by reluctance. So I am just writing down the final things. Okay, so you will see that L1 is N1 square by reluctance. Directly you can find if you know N1 square and reluctance, N1 value and reluctance value. L2 is N2 square by reluctance. Now this is basically the self part, okay, basically denoted by L11 and L22. Okay, now if we talk about M21 or M12, it is N1 N2 by reluctance. Okay, so like this. So you will see that we will be using this for solving our questions. Okay, this is important. Okay. So this is the uh, thing which is discussing something, but I think I have already discussed this. Okay. So now let us come to the questions quickly. So if we see the questions, questions are very simple. Okay. If you have understood the theory, you can solve the questions very easily. Okay. So just listen carefully. Now, before proceeding to questions, is there any doubt? Please tell me. So is there any doubt? I have discussed many things. So I have discussed lot of things. So if there is any doubt, so please ask. Okay, I'll be sharing these slides also. So you can just focus on listening and understanding. Okay, if that and you can and you may not write it parallelly because I'll share this. Okay, so just tell me if there is any doubt. So I'm proceeding ahead. Okay. So if there is any doubt. So I said that you do not have to write, but people are leaving. They do not have to understand. They have to understand at least, right? Okay. So let me then just proceed ahead with the questions. Okay. So you can use these questions to basically what you say solve the you will see these are the sample questions. Okay, क्योंकि exactly weak assignment questions we are not allowed to discuss because if we so because they have some marks associated with it, right? So I'll be discussing some of the sample questions which were given in the last year's assignment so that you can use it as a reference for solving this present week's question. Okay. So yes, Abhi Gupta is asking something. Please ask Abhi Gupta what you're asking. um, yes, Abhi Gupta, you're raising your hand. You want to say something? Have they mentioned it? They would have mentioned it, right? Like if you will see on the top, like where the assignment is given, you will see that on the top also deadline is also mentioned. I actually exactly do not know the deadline, plus but please check on the top or maybe on the site also it will be mentioned. Okay. So I'll be discussing the questions now, okay, so that you can use it as a reference for solving your present week's assignment. Okay, so these questions are generally more or less similar. Okay, only the values will be different, but the concepts will be exactly same. Okay, so let us start with this question. So in this question, they're asking that if the dot terminal is marked on this diagram on this part, so where should the dot be marked? Should it be marked on the top or should it be marked on the bottom? Okay, so we know that we have to apply Lenz's law now. Okay, in this question. So for applying Lenz's law, what we will do is we will first find that okay, if the dot is on the top, so if you will give the your supply like this. So if you give your supply like this, current will come out of the positive terminal. So current is coming out of the positive terminal means current is like this. Okay. Yes, it is like this. And then it is coming like this. Okay. So current is going like this. So current is going like this means again your magnetic field line is downward. Okay, so we know that because this magnetic field is downward, we want the magnetic field here also to be downward so that it opposes this magnetic field. Okay, so we want this magnetic field to be downward here also. So the magnetic field has to be downward means how the current should flow here? Can someone tell me the current should flow in which direction? Current should, so this direction is, if in this direction, it is basically your क्या कहते हैं clockwise direction, and this direction is anti-clockwise. So this is which direction? Clockwise direction or anti-clockwise direction? Currents. So someone has answered clockwise. Yes, clockwise. Correct. Rajan, both, any both of you are correct. Okay. So this is clockwise. So here this is clockwise. So the current has to be clockwise. So clockwise means the current is coming out from the C terminal. So if the current is coming out of the C terminal, so the dot has to be here. Okay. Is it clear? This is the exactly same thing which we discussed right now. So the dot has to be on the C terminal. Okay. So this was a very simple question. If you have understood the Lenz's law properly, you can easily solve these kind of questions. Okay. So the current has to be, so this is how you can find the current direction, and from the current direction, you can find the dot polarity. Okay. Now we go to the next question. Now, in this next question, so basically what they're saying is that they are saying that we are giving now a voltage supply which is having 500 volt as the RMS value. So they are saying that E1 is 500 volt. Okay, now they are saying that is connected between the terminals AB, 500 volt is given across AB, and CD is left open. Okay. So CD has is left open. Okay. Now they're saying that they're just saying coils are connected in series as shown in figure, just for your thing. It's nothing much. Okay. So basically what will happen is that the current will flow like this, and then the current will enter like this, and then the current will go like this. Okay. That is what they are telling by connecting this in series. Okay. So current is flowing like this. Okay. So now they are saying calculate the what you say value between A and C. So they are telling you to calculate the value between A and C. So first we will calculate at E2, and then we will calculate at A and C. Okay. So what will be E2? Because we know E1 by E2 RMS values are equal to N1 by N2. We have found this right from here. So from here we have found this relation. Same relation we are applying here. Okay. This one. This relation. Okay. This relation I want to talk. So now we coming back to this question. So we can directly apply this relation, right? So E1 is what? E1 is 500 and E2 is ECD basically. ECD or E2. So I'm writing both E2. Okay. So this is equal to N1 by N2. So N1 is how much? 100 and N2 is 200. So E2 becomes what? 1000 volt, right? So now let us see. So let us say that EAB, so EAB is basically EA minus EB is 500 volt, and E2 or ECD, EC minus ED is 1000 volt. Okay. Now what we have to find out? We have to find out EAC. Basically between the terminals A and C. EAC. So EAC is EA minus EC. Okay. And you will find that B and T, they are short circuited, right? Indirectly they are short circuited. So you will see that EB will be equal to ED. Okay, so if I have to find EAC, so what I'll do is I'll just subtract 1 minus 2. So if EAC we have to find, okay, we have to find between the terminals A and C. Okay, so let us do that. So EA minus EB is 500, and this is minus EC, because minus I have done like this. Okay, so let me write it in this way. EA minus EB minus of EC minus ED is equal to 500 minus 1000. So EA minus EB minus EC plus ED is equal to minus 500. So you can see that EB is equal to ED. So minus EB plus ED gets cancelled. So we are left with EAC, which is minus 500. But they are asking you, see, enter a positive number. Okay? So that specifically they're asking you to enter a positive number because they know that your answer will come in negative. Okay? So they're asking you to enter this mod of EAC, which is 500 volt. Okay. Is this question clear? Is this question clear? EAB is equal to EA minus EB. Okay. Whenever it is written like EAB, it means EA minus EB. Okay. And if they're asking you ECD, then this is EC minus ED. Okay. So it can be said that voltage between A and B terminals also, and they may ask you to find EAB like this also. Okay. Ah, so this is like this. You will see that this is the kind of convention which is followed everywhere. Okay, if someone is saying like between two terminals EXY, so this is like suppose this is. Oh, no, 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 no. You just follow like this. Okay, this is EAB like this. Okay. You will see that generally in the books, textbooks also they generally write like this. Like if we talk about potential, we are talking about potential difference, right? EAB and ECD, they are potential differences. So you will see that generally the potentials are marked like this, that the higher potential is marked first, and then the not higher exactly means the terminal between which you want to find, like this you want to find AB, so it will be like this. So if suppose this is AB, so they will generally write like this. Okay, that is what I'm following. Just check the book, like suppose which book you can see. Maybe you can see hmm? You can see you can see Bhimra also, or maybe you can see any standard books. Okay, they will generally see the potential difference like this only. Okay. Hmm. No, actually, I was thinking about some fundamentals of electrical engineering book like Hayat Kemerly, like that. Okay, so author name I know, but it is very basic. So this is Hayat Kemerly. Okay, like here basics of electrical engineering will be discussed, like potential differences and all. But if you want to follow electrical machines, for electrical machines, you can follow the PS Bhimra as you rightly pointed out, and the other book is Nagrath Kothari. Okay. Nagrath Kothari is little bit of a heavy book, but you try to read. It is a very good book for electrical machines. Okay. So these are the two books. And the Hayat Kemerli is for the fundamentals of electrical engineering, or basically fundamentals of basically electrical circuits book. Okay. So these potential differences and all these things, this will be properly discussed in electrical circuits book. Okay. So that is it. Now, this question is clear, right? This is a very standard question. It's very simple question, and for that is why for eliminating the doubt in, because see here in the question they have not marked anything, right? They have not said so if someone is saying between the terminals A and C, someone can take it as EAC, someone can take it as ECA also, right? अब बिटवीन तो कुछ भी हो सकता है, ए और सी के बीच में भी हो सकता है, सी और ए के बीच में भी हो सकता है, तो बिटवीन तो दोनों के लिए फॉर द बोथ इट इज वैलिड, राइट? So that is why, to eliminate the confusion, they have asked you to enter a positive number. Okay. So if these kind of ambiguous questions are there, then they will definitely mention something. Okay, that enter a positive number or something like that. So don't worry. Okay. Now coming back to this, is there any doubt? Is there any doubt? So please speak up. Um, like how he spoke up, please speak up. Okay, this is a basically doubt clearing session only. If you get your doubts cleared, then you can solve the questions, right? So I am just then going ahead. Okay. So now the same thing will be continuing. Now you see the inductance questions have come. Now here they are asking, so they are saying that, so in the question, in the data they have mentioned that self inductance of coil AB, let us say this is primary coil 1 and this is secondary coil. So L11, they are saying that the self inductance, right? So self inductance, which is equal to N1 square by reluctance, is equal to 1 Henry. Self inductance of coil AB means L11. Mutual means 1 2, with 1 2 we do not generally L12 or M12 like this. Okay, M21, M21, L21 like this. Okay, so generally mutual is denoted as 1 and 2, 2 1, and self is noted by 1 1 notation, 1 1 or 2 2. If suppose it is on the secondary, then 2 2. So here you see I have mentioned the inductances values also, right? Here. So this is what I have written. So they are saying in the question that the self-inductance of coil AB is 1 Henry. So self-inductance is L11, which is 1 Henry. Now they are asking you find the self-inductance of coil CD, which is L22. So L22 is N2 square by reluctance. Now you see something, you will see something very interesting. Okay. So the interesting thing is that the reluctance for both the coils, reluctance is what? Reluctance is basically the, so the reluctance is given by, so this is, so let me use some other color, I guess. Otherwise it will be confusing. Okay. So so reluctance is basically the magnetic path length. So magnetic path length is, let us say, Lg. Okay. So reluctance is Lg by nu naught nu r, matlab relative permeability of this magnetic medium nu r. Nu naught is the permeability of air. Okay, so permeability is air is like 4 pi into 10 power minus 7 units. I'm not remembering, okay, right now. So it, there is some units here also. So Lg by nu naught into nu r by a cross section. So a cross section is what? Cross section basically, this cross section. Okay, so this cross section. Now for, if suppose, so this is the cross section. Okay, so you see for these magnetic field lines. Okay, if suppose the induct, if suppose the if suppose you put the voltage source at the input, so what will happen is that the magnetic field will be produced due to the first coil. So the magnetic field produced due to the first coil will see the reluctance of what? Because the total path length of this first, for the first case is what? So the total path length is basically same Lg, Lg by nu naught into nu r by into AC. And for the second coil also, the path length will be the same, right? For the magnetic field Lg, and the cross section is same, magnetic medium is same. So you will see for the self inductances in both the cases, in the first case and the second case, so R1 and R2, they are same, right? Is there any contention to this? They are same, right? R1 and R2, because it is the same magnetic medium, it has the same cross sectional length, right? It has the basically same length of the magnetic field. So that is why this reluctance here and this reluctance here is same. Okay, so if I take the ratio of L11 by L22, it becomes N1 square by N2 square. So this is 1. Okay, now we can find out, right? So L11 by L22 we can find. So L, so L11 by L22 is equal to N1 square. So N1 square is 100 square, N2 square is 200 square. Okay, so L22 will be L11 into 200 square by 100 square. So which is L11 into 4, and L11 they have given as 1. You see here. So this is 1 into 4, 4 Henry. Okay, is this clear? These are very simple questions, but they have lot of, they have concepts in it. Like you see directly they are telling you the answer, but if you see the concept, you will see that okay, the basically the reluctance for both the cases is same. That is why you can do it like this. Okay, you can take the ratio like this. Okay, now coming to the question, next question here. So in the next question, they are asking you to find the mutual inductance between the two coils. So they are telling you to find L12, L21 is equal to N1, N2 by reluctance. So we know L11 is N1 square by reluctance, which is given as 1 Henry. Now again we will take the ratio of 2. L21 by L11 is equal to N1, N2 by N1 square. So 1 N1 and 1 N1 will get cancelled here. So it will be so L21 will be L11 into N2 by N1. So L11 is 1 Henry into N2 is 200 by 100, which is 2 Henry. Okay. Is this clear? These are very simple questions. Nothing tricky in this, just direct mathematical manipulations. Okay. So I hope this is clear. So at any point of time you have doubt, please stop me in between and ask the doubt. Okay. Now going to the next question. Now in this next question, now this is some interesting question right now. Okay. Now they are saying that okay, if suppose 3 ampere DC is passed through the two series connected coils, then how much electromagnetic energy in joules will be stored in the two coils? Okay. So what is the formula of energy? I am writing down right now. Okay. So let me write down. So energy is basically half L1 L11 I1 square plus half L22 I2 square plus minus M12 I1 I2. Okay, so this is the basic form of the energy formula. Okay, now you see whether this is plus or this is minus. This you have to decide depending on the dot notation. Okay, so you will see that. So you have to find the effect of the mutual inductance, whether the mutual inductance is additive in nature or whether the mutual inductance is subtractive in nature. If it is additive in nature, then the energy becomes half L11 I1 square plus half L22 I2 square plus M12 I1 I2. And if it is subtract, so this is additive mutual inductance. Okay, additive mutual inductance. If it is subtractive, then it becomes minus. Okay, so now let us see whether this is additive or subtractive depending on the dot notation. So you see current is entering the dot here. Current is going like this, like this. So current is now traveling here, 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 then here, here, and current is coming out. So if the current enters in both the dots or if the current leaves both the dots, then it is additive. Okay, so I am writing current entering, leaving both dots. If current is entering in one dot and current is leaving in other dot, okay, then it becomes subtractive. Okay, it means current entering in one dot and current leaving in other dot. Okay, so you can see that in our case, current is what? current is basically, for this dot it is leaving, but for this dot it is entering. Okay, what happened to this? So this current is entering the dot, right? First the current was flowing like this and then it was entering the dot, but here the current is leaving the dot. That is what is the transformer action or the Lenz's law, right? Because the Lenz's law said what? The Lenz's law said that this flux due to this coil and flux due to this coil should oppose each other. So it means subtractive, opposing. Okay, so that is why you will see that in our case, the you will see that this is how, for the added, for this is subtractive in transformer action. Okay, so the energy becomes like this. Okay, so this is how the energy becomes. So you see, because this is connected in series, so 3 ampere is flowing here, means 3 ampere is also flowing in I2. So I1 is 3 ampere, I2 is 3 ampere, L11 is given as 1 Henry, L22 we have found from the second question, third question I guess, as 4 Henry, and from the last, just previous question, we have found L12 or M is 2 Henry. So you just place everything in the formula here. So half L11 is 1 into I square, I1 square, plus half L22 into, yeah, I2 भूल गए, I2 square, half L22 into I2 square, minus, because transformer action, Lenz's law, subtractive mutual inductance, M, which is 2 into I1 into I2. So if you solve this, you will get it as 4.5 joules. Okay, is this question clear? So I hope this question is clear. Okay, so I will just assume that these things are okay unless someone speaks. Okay, you have to speak up for, or maybe write in the chat if you have doubt. Okay, so now going to the next problem. Hmm. क्या हो रहा है? Okay, somehow my screen is having some issue. Okay, let me just do this. Okay, because actually I'm not getting that pen option in between for some, due to some reason. So let me just hide this, I guess, and then do this. Okay, so I'll maybe use the okay, so what to do? Mm. Okay, just let me open this PPT again. Okay, I think there is some issue there. Okay, so let me just open it. Just wait for some time. Mm, E drive, NPTEL, Machines 2, Assignment 1. Okay, so let us just see. Now it is coming. Okay, so coming here. So this is the next question. Okay, so this is the data for the next set of questions. So here they have given you two circuits. Okay, now they are saying that all inductances are basically uncoupled, so are pure without any resistance. So they are asking you that, so this is the primary side inductance, this is the secondary side inductance. Okay, so they're asking you that what, so what will be the primary side inductance, secondary side inductance, not basically primary. So this is, so see, this is the basically what you say, two coupled inductors. Basically they should say not uncoupled, they should say coupled. Actually they have mentioned it wrong, they're coupled inductors, right? Because they're mutual inductance. So this is coupled inductances, which is on the primary side as 8 Henry, secondary side is 7 Henry, and this is the mutual inductance between them. Now if they have to draw it in this form, in this LP LQ LR form, then what they have to see is, they have to see that what is the value of this LP, what is the value of LQ, what is the value of LR. So this is the question. Okay, so here you see, so in this here assignment, so let us try to solve that. So so this is basically like a two port network. Okay, so for the two port network, basically what we do, we generally assume that the current is basically entering both the ports. Okay, so we are assuming that okay, v1 v2 are positive terminals like this, and i1 i2 are entering the two ports. Okay, just this is just the convention of two port network. Someone can say that okay, we could have taken the convention of transformer like i1 entering i2 leaving, but we are actually following the convention of two port network. Okay, so we are following the convention of two port network, because this is not a transformer, right? This is just two basic circuits. So basically this is like a black box. This is a black box which you are representing it like an another black box. Okay, so these are the two ports which are coming out of these two black boxes. So it means that this is a problem of two port network. So convention of two port network is basically currents entering the two ports, currents entering both the ports, and positive terminal on the upside. Okay, so this is what the convention is. So now we are saying that okay, v1 v2 is like this, i1 and i2 are entering the two ports. So similarly for this black box also it should be the same, because they are both the same circuit. Circuit 1 and circuit 2 represent the same system, right? So i1 and i2 are also entering the two ports here like this. So if I write the kvl here, so what will be the kvl equation? So kvl is like this: v1, and in the direction of the current, suppose that this direction of current is like this, right? This is the direction of current. So v1, in the direction of current, the voltage is dropped across the inductance. Okay, so the drop means that we are entering the positive and we are leaving with the negative sign. So this is minus, because the potential is dropped across the inductance or resistive elements. Okay, v1 minus j omega, because we write xl into i1, so xl is j omega l into i1, right? That is why it is written as j omega, and what is the value of inductance? 8 into I1. And remember, the effect of mutual inductance will also come here, right? So even if so it is like this. Okay, so you will see that here, the even though I2 is not flowing directly here, but due to this mutual coupling, this effect will come. Now, how will this effect come? So because you see, so in both the dots, the current is entering, right? So current is entering in both the dots means, so this L1, so this mutual inductance M12 should support L11 and L22. Means whatever is the direction of L11, it should continue in the same direction. So here the direction was negative, so here also it should be negative. Okay, minus j omega. uh, so here it is minus j omega, and what is this? 1 into I2 equal to 0. Similarly, for the second this coil also you can write the KVL. So here it will be V2 minus j omega 7 into I2, and because mutual are supporting the inductances, so this supporting means with minus, so this is also minus. Okay, supporting means same sign as this. Okay, so this becomes j omega 1 into I1 equal to 0. So these are the two equations which are, so if you take this on the these two things on the other side of the RHS, it becomes the same thing. Okay. Now for the circuit 2 also we will write the same, what you say, this KVL equation. So this is I1, this is I2. Now in this coil it is I1 plus I2. Okay. So here in this coil it is I1 plus, also in this conductor it is I1 plus I2 due to KCL at this point. Okay. So due to the KCL, the current I1 and I2 are added up to give I1 plus I2 here. Now if I again write the KVL for this circuit 2, so it will be like this. So this is for circuit 1. So I am writing for circuit 2. So for the circuit 2 it will be what? V1 minus j omega. So j omega LP into I1, j omega LP into I1, because it is dropping like this in the direction of current. Then in this it is minus j omega LR into I1 plus I2, because through LR both I1 plus I2 is flowing in this path, right? This is the KVL loop. Now this is the other KVL loop. So for the other KVL loop, it is V2 minus j omega LQ into I2 minus j omega LR into I1 plus I2 equal to 0. Okay. So now, because see, these two circuits represent the same system, so these KVL equations should also be same for the both the systems. So let us now compare the coefficients. Okay. So now if I club the coefficients of I1 together, so if I club the coefficients of I1 together, it becomes like this. So V1 minus j omega LP plus LR into I1, right? Because this I1 is common in both with the LR and with the LP. So that is why this is LP plus LR. And with the I2, this is j omega L2 I2, LR I2. Okay. Then for the V2 case also, if I write the equation, so if I write the equation, so there is I1, so I1 has only LR part, this I1 has only LR part, and this I2 has both LR part and the LQ part. That is why LQ plus LR into I2. Now you have, because these two equations represent the same system. Okay, so that is why what we will do is we will just compare the coefficients. Okay, so you see the coefficient of I1 is 8. So 8 is equal to LP plus LR in this first equation. This coefficient of I2 here is 1, which is equal to LR. Coefficient of LR here is also 1. This is equal to LR. And coefficient of LQ plus LR is 7. So LR is 1 from this calculation. LP is LP plus LR. LP plus 1 is 8 means LP is 7. And LQ is 7. LQ plus 1 is 7 means LQ is 6 Henry. Is this question clear? So you see we have solved for the three things. So in this thing, the LP they have asked, so LP is 7 Henry. Okay, here in this question. Now for this LQ we have found out, so LQ is 6 Henry and then LR is 1 Henry. Right, so three questions are simultaneously solved. So you will see that, okay, we have to write two KVL equations for the two circuits again and again. It's a lengthy question, but you will understand that if you solve this question completely, you can solve three questions, which are the three parts. Okay, so don't worry if it's you see that the time is being taken. Okay, the time is utilized for you to solve the three questions together. Okay, so don't worry. Is there any doubt in this? Is there any doubt? This is a very good question. Okay, so this is the only part I think is a little bit tricky. So you can just see. Okay, so if there is doubt, so please speak up. Now going to the other two parts of this question. Now they are asking that if suppose in this circuit one, if in circuit one, if we connect a 150 volt RMS, so they are saying that if we connect a 150 volt RMS here, 60 hertz AC source. Okay, then how much current will be drawn from the source. So what will be this I1? Okay, because this circuit and this circuit are the same, you can connect this 150 volt RMS to this circuit 2 also, right? So this is open circuited, right? So current will not what you say flow through the open circuit path, so it will flow through a closed path like this. So what will it will see? So current I1 will see the impedance of 150 by divided by you can say x x7 Henry plus x1 Henry, right? So this will be the current I1. Now what is this? 150 by j 2 pi 7 plus j 2 pi 1 into 60, because inductance omega L, right? J omega L is inductance. So J into 2 pi, and they have mentioned in the question as 60 hertz. Okay, so you have to take it as 60. Okay, so that is by 60 is taken, and then the value of inductance. So inductance value was 7 for this inductance, and this is 1 for this inductance. Okay, so they are asking you to find the RMS current. Okay, so RMS current means we have to take the magnitude. So we don't need to bother about the J component. So you can just take it like this. So because the real part is 0, so root over of real square plus imaginary square. So real square is 0 means this becomes 150 by whatever is the imaginary part. So this is 2 pi 60 into 8. So if you substitute this, you will get this much value of current. But in the question, please read the question carefully. They're asking you to enter the value in milliampere. So 0.049 ampere means 49 milliampere. Okay. So you have to enter this value. So is this question clear? Now we will see the last. Yes, yes. So you are clear, right? What is your name? Kali. Kali is your name Kali or Kinkar? Kali Kinkar. So both is so Kali Kinkar. Okay, so it's clear, I guess. So let us go to the last question of this assignment one. Okay. So last question or acha, I have missed some questions. No, no, I have not missed. This is basically the things which I have already discussed together, right? Now we are going to the last question. Now in the last question, they are saying that they are shorting this CD terminal. Okay, so if suppose you in earlier question you kept the CD terminal open, but now you're keeping the CD terminal shorted by applying this 150 volt 60 hertz voltage source. So you can see that you are applying 150 volt 60 hertz voltage source by keeping this shorted. Okay, so this is equivalent to applying this 150. So here you are applying in this circuit 150 volt 60 hertz, but this is equivalent to applying it in circuit 2 because they are both identical circuits, right? They represent the same system. So that is why they have connected in this circuit. So for this circuit they have connected. That is why you see actually you if you read this what you say two port network, so you will see that this is basically T model representation of the two port network. There is pi model representation also. So generally you will see that these kind of circuits like having mutual inductances and these are generally converted to T model or pi model because it becomes very easy to solve these questions. Like you see this is so you did not even have to think, okay, right, okay, what is the mutual, what is this self. So if you are asked in this circuit, it will be difficult to find, right? But it's not, you can find still by using the KVL equations. But this in this equation in this circuit you can directly imagine, right, how you can do the parallel connection, series connection, like that. Okay, so that is why generally in two port network you convert the things into equivalent pi model or T model. So this is a T model. Okay, so now you see here we are shorting these CD terminals. So, so shorting the CD terminals means this 6 Henry and 1 Henry becomes parallel. Okay. So this, what is the current I1 which is now being drawn? So I1 is equal to J 2 pi 60 into 7 Henry plus the parallel combination of this 6 and 1. So parallel combination means 6 into 1 by 6 plus 1, right? This is the parallel combination. So parallel combination of L1 and L2 becomes L1 into L1 by L1 plus L2. So this is what I have written, the parallel combination. Okay. So again, if you write the RMS value, so RMS value will come out as, because 150 by the magnitude of this complex number. So magnitude of this complex number, you can just write for the imaginary part like this. Okay, 6 by 7. So if you solve this, you will get the answer this. Okay, and this is in ampere, but they're asking in milliampere here also. So you have to enter this 50.64 milliampere. Okay. So that is it for this assignment one. Is there any doubt till in the questions, in the concept anywhere? Is there any doubt? So Raj, you have any doubt? If you're speaking, then your voice is very low, Raj, है ना? Your voice is coming very low for some reason. Um, so can you just write in your chat box? Actually, when you spoke, it was like very feeble, your voice. Okay. Can you write in the chat box? So other people, have you any doubt in whatever we have discussed? The theory, the questions, two-port network problem. Okay, so in two-port network problem means which question? So this is the sixth question. Sixth question or the last two questions, ninth or tenth? Which question you have doubt? Sixth question or nine, ten? Can you specify? Sixth. Okay. So in the sixth question, what is your doubt? Is your doubt in the KVL equations? What is your doubt there in KVL equations? Should I repeat it? So should I repeat the sixth question KVL part again? Rajkumar, should I repeat it? Can you write yes or no if I should repeat? Okay. So I'm writing. Okay. So you see. So here, basically, this is a two-port network, right? This is a very standard fundamentals of electrical engineering two-port network question. Okay. Now, generally, what they ask you is, they give you this kind of circuit, and they ask you to find that either the T model representation or the pi model representation of this circuit. Now, you can appreciate that why we represent it as T model or pi model is because you see we were able to solve these questions directly, right? So for solving these questions, for doing this analysis, we generally represent this kind of what you say coupled circuits in T model and pi model. Okay, so you can appreciate that after solving the last two questions. So in this question, basically what we are doing, we are writing the KVL. Okay, so for writing the KVL, so here this is our first loop. Okay. So for the two-port network, we generally assume the currents going into the from the into the two ports as the convention of the current direction. Okay. So and positive terminal at the top. So we are writing the KVL loop. So we are starting from here. So we are moving from B to A. So we see a rise in the potential. So this becomes plus V1. Okay. Then in the direction of current I1, you see in the direction of current I1, what is happening? The potential is dropping across the inductance, right? Because it is a passive element. So the potential will drop across the inductance in this way. So let me write it. So it will drop like this. So in the direction of current, it will become V1 minus because it is dropping, right? From plus to minus. So minus j omega 8, basically j omega L into I1 because I1 is the current. Okay. Now, what to do about the mutual part? So for the mutual part also, what will happen? Because you can see that they are both additive, right? The mutual inductance is additive in two cases because in both the dots the current is entering like this, right? So current is entering in dot means it is a additive mutual inductance. Now, what do this additive mutual inductance mean? Okay, it means that if suppose if you apply the positive terminal here, so you will get the positive terminal here. Okay, so it is something like this. So I'll draw it separately here. Then I think this is your doubt. Okay, so this is the dot. So if you apply positive terminal here, so you will get positive terminal here like this. This is for the additive. Now for the subtractive, it will be something like this. So this is the dot, this is the dot. So if you apply positive here, so you will get positive at the bottom and negative at the top. So what is happening, because this is additive, so in the direction of current, the effect of the mutual inductance is also like this, right? In the direction of current, the potential is reducing from plus to minus. That is why I wrote it as minus j omega into 1, which is the mutual inductance, into I2, because of the I2 current, the mutual induct voltage is coming here. Mutual voltage polarity is what? Because it is dot additive. So if the dot has plus, so the dot should also have plus, and at the bottom it should be negative, minus. So it means what? In the direction of current, the potential is dropping for this additive polarity of mutual inductance due to the current in I2. That is why here it was minus. For the similar logic, you can see that here also, if we are writing the KVL, it is V2 minus I2 j omega, because here it is dropping like this, plus here minus here, so the potential is dropping in the direction of current. So minus j omega 7 into I2 minus, but why this is minus? From the same logic, because this is additive polarity. So if the positive is here, because in this direction the current, because for this positive is here, right? So if positive is here, means positive effect also comes here due to mutual, and negative comes down. So in the direction of current, this mutual inductance is also having a drop in the potential. That is why minus. So in this way, the two KVLs are written. Now for circuit 2, it is very simple. Circuit 2 is just straightforward, right? Because V1 minus LP minus j omega LP I1. So this is the path. Minus j omega LP I1 and minus j omega LR into I1 plus I2. Because if I apply KCL here, so this LR will have I1 plus I2 current. Then here for the CD, it is what? V2 minus j omega LQ into I2, because in the direction of current it is like this. And then here for LR it is I1 plus I2. So minus j omega LR into I1 plus I2. Now you compare these two equations and you see what all coefficients are common for I1 and I2, and then you can just arrive at these things. Okay. Is it clear? Okay. ठीक है. So I think if this is clear, so that is it for this class. So I'll share these notes to NPTEL people, and then they will share you some, what you say, link. Okay. So they will give you some Google Drive link. So in that, if you go in that Google Drive link, you will find the link for the basically the recorded video lecture also, and also you will see these PPT slides also. Okay, so you can go through it. And the other thing is that the next week I will be actually this class is supposed to happen every Saturday 5 to 7, but next week actually I have to go somewhere. So maybe this class will happen on Friday 5 to 7. Okay, so NPTEL people will confirm this for you, and maybe they will basically share this information with you if this is confirmed. Okay, so instead of Saturday, maybe we may have the class on Friday 5 to 7. Okay, next week. So that is it for this week. If you do not have any other doubt, so I'll be stopping the session here today. Okay, so yes, tell me. Okay, just let me just listen. Instead of first, so you see, this is January, right? So the next week is supposed to happen on first Saturday. So instead of first on Saturday, I'll be taking the class on 31st. 5th February only. I'll be taking the class on 31st. So I don't think it will be a problem, right? If I discuss it earlier. If it were later, then it would have been a problem, right? Then you would not know the sample questions. But I'll be discussing it earlier, like 31st. Yes, yes, sir. So yes, yes. Okay. Oh, no, actually the thing is that the pattern is same. You will see that this week assign. Ha. Okay. Ha. Hmm. So they are there. No, actually what is happening is that, you see, what happens is that basically the electrical machines too is focus is on synchronous machine and induction machine. But for some reason in the first week, week 1, sir has discussed some things associated with the mutual inductance, self inductance, and the transformer. For some reason, actually this is part of electrical machines 1. Basics. Oh, that is the problem. So, what kind of questions are there in the assignment 2? Can you just tell me? The conductor questions and these kind of questions are there. Okay, okay. So, I understand. So, what is the date of submission of this assignment? Assignment 1? Can you just tell? Fifth, fifth only, right? Assignment 1. So, don't worry because most probably, okay, okay. So don't worry, okay? Because what will happen is that maybe I'll discuss that because I discussed these things, and I took some time. So what will happen? I'll may discuss this conductors part and all these parts, which may be related to your assignment 1, that questions, okay? Which you're talking about. So I think that will not be a problem, okay? Okay. So the next class, maybe I'll discuss with these people. It will happen on 31st, 31. So maybe in these classes I'll discuss about the conductors and these things because that is what how it will proceed to synchronous machines and induction machines. First they will discuss with a single conductor and then they will extend it to machines. Okay. So that is it for this assignment. So if there is any other issue, then you can discuss. Otherwise, I'll be stopping the class today. Okay. So I think that is it. So I'm stopping the class. So I'm stopping the presentation. Then okay, then we can stop the class today here. Okay. So then I'm leaving. You can also leave. Okay. Okay then. Thank you. Then I'm leaving. Okay. You can also leave. Okay. Okay then. So I'm leaving. Okay. We will meet on 31st Friday. Okay.